we will take some applications of diode in a circuit. Basically, there are 3 or 4 uses for the normal p-n junction diode. The one is diode as a rectifier, diode in clamping circuits which are known as clampers, and diode in clamping circuits which are known as clampers. So, rectifiers, clippers and clampers, these are the 3 basic uses of a diode, and we will talk about them one by one. First, we take diode as a rectifier. Rectification is the process of converting a AC voltage into a DC, or AC current into a DC current, one and the same thing. We can talk either in terms of voltage or in terms of current, but often it is preferred to talk in terms of voltage. So, rectification is the process of conversion of AC voltage or current into a DC voltage or current. This is the process of rectification. Let us see how a diode acts as a rectifier. Let us consider a simple circuit. We apply a AC signal here. This is the voltage axis and this is the time axis. So, this is the AC signal which we are applying here, and what will happen? This positive cycle, the positive part of the input signal, that will forward bias the junction. That means, by forward bias, again I remind that this terminal, the anode, has to be at higher potential than this terminal which is cathode. So, this will be forward biased by the half cycle. If we consider the diode as ideal, then the current will flow and the output will give a voltage here. So, when it conducts, there will be a current and there will be a voltage drop. In this part, in the negative half of the input cycle, this will become a reverse bias diode, and if we consider it ideally, then the resistance is infinite. So, there will be a break in the circuit and the current will be 0 in the circuit, and hence the voltage drop will be 0. So, under this condition, the output waveform, this is the voltage, this will be like this. Like that. This is time, or many times we plot actually omega t in terms of angle. So, this is 0, pi, 2 pi, 3 pi and so on, or in terms of time, this point will be 0, here t by 2 and here it will be t and so on. This is the output. This is that means the output is not pure DC, but it is pulsating kind of voltage which will rise from 0 to a certain value, then drop to 0 again for half period it will remain 0, again it will rise. This is called half wave rectification, half wave rectifier. Obviously, because out of this complete wave, in the output it is only the half, that is why it is called half wave rectifier. Now, if we consider this as ideal, then if the peak value of this voltage is Vm, then this peak value will also be Vm. If we take the practical diode characteristics, then out of this Vm there will be 0.7 volts drop across this and remaining one will be here. In that case, the peak value will be Vm minus 0.07 volts. So, this is the half wave rectification. Rectification is a very important property. There is no electronic circuit which does not require the DC voltages for biasing a electronic device, as when we study a bipolar transistor, which is simply called BJT or transistor, then we require DC voltages to bias the junctions. If we are using field effect transistors, then we again require DC voltages to bias the FET. So, every electronic instrument requires a DC voltage, and DC voltage of course can be provided by batteries, but you know they are expensive, bulky. So, unless there is a portable instrument, portable circuits, then we may use DC. They will not require any further rectification, but most of the devices like at home what we use, music systems, transistors, cassette recorders, tape recorders, television or computer, they all require a DC source, and and the power we supply is from mains. So, we have to use a rectifier, and before that we have to use a step down transformer, because these circuits will be actually rectifying smaller voltages, say from 5 volts to 30 or 50 volts. So, this is half wave rectification, not of much practical use, because it will have a very high portion of ripple. Ripple is what is the fraction of AC by the total DC. So, there is a small portion, a large portion of AC also here. So, this half wave rectifier is not of much practical value. If we use 2 diodes, then we get what we call a full wave rectifier. Full wave rectifier that makes use of 2 diodes. Here this is a step down transformer. For which the primary is connected to 220 volts AC, and how much we have to bring down this voltage, that depends how much we want to use. In many devices, for example, 5 volts is required, or 10, 30, 40, 50 volts. So, we will use a appropriate transformer with central taping. This is a special transformer which is having central taping. That means there are 3 connections on the secondary side. These 2 which are normally there in every transformer, but here there is a third terminal, the central connection from the half of the turns on this side, upper side, and half are there on the lower side. So, this is the transformer which is made use in this full wave rectifier circuit. Now, for when this, let us see what happens in the upper half of the input signal. This is the plus terminal, minus, plus, minus. Therefore, diode D will be conducting, while diode D2 will be off. So, D1 conducts is on, diode D1 conducts, or as it is called, this is on diode, and this is off. D2, diode D2 is off, it does not conduct. So, this will, the current will flow, this is a very high resistance. So, this will ignore this path and it will go, the current will flow like this. In the upper, when this changes, that means we talk about this lower half, then the connections will be like this. Now, this will be minus opposite of this. In this case, this diode D1 will be off, and it will offer very high resistance, ideally infinite. So, we can take the circuit is discontinuous here, but D2 will be forward bias. And this will be on. Therefore, current will flow this way. This is infinite resistance, will avoid, will not see this diode, and current will flow this way. That means, for the whole cycle, the current flows in the same direction in the load. R is the load. Load can be any device like tape recorder, for example, and so then this will be the resistance, the input impedance of that device that will act as a load. So, what will be the output waveform? When this is the input, for this input the output will be now and so on. This will be the output. For obvious reason, this is called a full wave rectifier. A full wave rectifier, and this is 0, pi, 2 pi, 3 pi if this is omega t, and if it is time, then this is 0, this is t by 2, this is the period t, and so on. So, this is full wave rectifier, that means both halves are converted into a kind of DC. DC means that current flows in one direction, but actually this is full wave rectifier. Still the output is not very smooth. This voltage wave, this can be actually seen as containing a DC part and a AC part. Here this is the AC part, and there is a DC part. This is the equivalent voltage as a function of omega t, and there is a DC part here, DC voltage, and the ratio of this AC by DC is known as the extent of rectification. And there is a ripple factor. So, this is the ripple factor. So, there is still a ripple, and in many applications this will be acceptable, so much ripple, because it will be a cheap circuit, very economical, just use of 2 diodes and that makes with a transformer, centrally trapped transformer, that makes what is known as full wave rectifier. But in many applications, in fact in most of the applications, this ripple is not acceptable. For that we use filters. Filters, there are several kind of filters, like inductor acts as a filter, capacitor acts as a filter, and the combination of the two, the most widely used filter circuit is what is called pi filter. I very briefly talk about these filters, and then we will, because this is not the part of the PN diode actually, but since we are talking of the circuits, so I very briefly talk. The inductor filter, inductor is used here. This is the rectified output is connected as the input here. This contains DC plus AC. Now, here this is V out, output. This inductor, you know that its impedance for AC is omega L. Omega is the frequency and L is the inductance, and for DC, that means the DC resistance of the coil is very small, and AC there will be a very finite, in fact large resistance will be offered by the inductor. Therefore, there more DC will pass to the output, while AC will be prevented by this inductor, and there will be a AC voltage drop across this, that is the AC part is drastically reduced in the output, and that has been taken care by the inductor. Similarly, so remember that inductor filter is used in series, and similarly we can use a capacitor in shunt connection. Here is the V0, and this is again the same DC and AC. That means that rectified output is given as the input to this filter circuit. Now, the impedance of this capacitor is that varies with j omega c. So, for AC this will act as a very low impedance path, and AC here it is DC plus AC, while AC will find path here and this will be prevented from going to the load. So, this is a much better, much smoother output waveform available to the load. When these two are combined, that is the best rectifier, and which is known as pi rectifier, pi filter, which is like this, that makes use of one inductor and two capacitors. Here the input from the output of the rectifier circuit, and here we get V 0, C 1, C 2 and L. So, first the AC finds a path here, it is filtered, then AC is obstructed by this inductor again, and whatever remains, that goes, the AC part goes here. So, here we get almost a very smooth DC. This is omega t, and we get very smooth DC voltage. So, this is DC voltage. Most widely used filter circuit is pi filter to get a smooth DC, which is required in most of the applications of in electronic circuits. Now, this was full wave rectifier, which made use of a central taped transformer. Central taped transformer that creates sometimes problems. Sometimes the central connection is taken out, many times it is not exactly symmetrical in the center. So, there are problems. Is there a way to get rid of this centrally taped transformer in the use of full wave rectifier? The answer is yes, and we make use what is known as bridge rectifier. Bridge rectifier is also a full wave rectifier, but it, as you will see, I draw the circuit, it makes use of 4 diodes and a transformer without central taping. This is the circuit. This is the transformer, and there is no central taping here, but there are 4 diodes D1, D2, D3 and D4. In the, now this is AC. Through this transformer we get a smaller voltage according to our requirement, but that is still a AC. As you know, that transformer steps down the magnitude of the voltage. but still it gives a AC output. So, for this signal, first we take what will happen in the upper half. This will be positive, this will be negative. Now, in this case, two diodes will conduct. This becomes forward biased and this terminal is connected to negative, one and the same thing. That means, this side is still at higher potential than this. So, this also becomes forward biased. So, for the upper half diodes D1 and D2 conduct. So, the current will flow like this, from here goes here, here and so on. So, this is the way the current continues, here, here, again like this. This will be the total path. And when this voltage for the lower half, the polarities will be like this. Now, for this lower half, this one, this diode will conduct D3 and D4. This is now minus and this is minus, this is plus. So, these will be reverse bias, D1 and D2, D1 and D2 they will be off, diodes D1 and D2 will be off, while this negative will forward bias this diode D3 and this positive will forward bias diode D4. So, diodes D3 and D4 they are on, they conduct and the current goes like this. Here so, this is the path current will take. For the upper half, positive half, these two diodes will conduct, they will be off, and for lower half these two diodes will conduct and this will be these two will be conducting, these two will be off. So, current flows always in one direction through the load and the output, as in the full wave rectifier, here also the output will be containing both and so on. So, this is again a pulsating DC which will require the filter circuit which we just discussed. So, this output is connected to the filter here and output of the filter will be very much DC. This is much better as compared to full wave rectifier. By the way, this circuit is full wave rectifier. This is a full wave rectifier and it is called a full wave rectifier. That means, full wave rectifier circuit makes use of two diodes D1 and D2 and a centrally taped transformer, while this is also a full wave rectifier, but popularly to distinguish between the two, this is always called a bridge rectifier. So, remember that bridge rectifier is also a full wave rectifier, but to distinguish between the two, this is called bridge rectifier. This is much better as compared to the centrally taped transformer full wave circuit, and basically at two biggest uses or rather advantages, two advantages will this has this bridge rectifier. Number one is does not require central taped transformer. Second thing is what we call peak inverse voltage. Peak inverse voltage PIV. That means the diode is subjected to the maximum reverse voltage during the cycle, that is known as peak inverse voltage, and there is a limit, and we will find that peak inverse voltage in this case, for example, when this diode is not conducting, the available output is V0, but the total voltage will be dropped across the non-conducting diode. So, PIV in this case is double of that available voltage. If we get a 5 volts here, then peak inverse voltage in a full wave rectifier will be 10 volts. The diodes which have higher value of PIV, they are more expensive. So, but in bridge rectifier we will see that this is PIV in this is much lower. First thing is whatever voltage we are getting, say V0 and these two non-conducting diodes will share the reverse voltage. So, in this case half will drop across this, half of will that drop here. So, the PIV in this case is much smaller. This will be P0 by 2, which is a much better factor as compared to the full wave rectifier. So, these are the two basic advantages of using a bridge rectifier. So, bridge rectifier actually is the one which is most widely used, and most widely used filter circuit is a pi filter circuit, which makes use of one inductor and two capacitors. So, that makes use that completes our this rectification process and the use of diodes in rectifiers. And remember, these two advantages are very big advantages. Then the next circuit application is in clippers. Clippers. Many times in the electronic design systems, we require circuits to restrict the amplitude of a signal. That means we want to chop off, we want to cut the upper portions of the voltage beyond a certain reference voltage. These are known as clippers. Clippers are used in restricting the magnitude of a wave, and for that diodes are used. So, let us look at this circuit. Here we are feeding AC signal with a peak value Vm, and this is the load. Now, this will chop off the lower portion completely. That means, this upper half will forward bias the diode, current will flow, and we will get a voltage across the load, and this will be V 0. In the lower half, the minus plus polarity will be there. This diode will be reverse bias, this will be open circuit, no current will flow, and the output will be 0. So, the output will contain, actually this is almost, this is a half wave rectifier, where from the input wave these lower halves have been clipped, completely removed, and this voltage, if we consider this ideal diode, ideal characteristics, then this will be same as the peak value will be Vm, and if we consider a practical diode, then 0.7 volts will drop here, and then the peak value, this will be equal to Vm minus 0.7 volts. Similarly, we can reverse it, and we will have, this is negative clippers, and if we change the direction of the diode and we feed here AC signal, then this positive will reverse bias this diode, and in that case the output will be like this. These are actually series clippers. There are parallel clippers as well, as you see to this circuit. They are very widely used. This is R. Now, for the upper half, this will be plus, this will be minus, and the diode will be reverse bias, it will not conduct, and the output will be, so it will not conduct, and the current will flow. This is infinite resistance. So, this is almost as if not present in the circuit, and this wave shape will appear here. If we reverse the direction of the diode, then of course, this will be the case. The upper half will give this polarity, it will be conducting. Conducting means almost 0 resistance. Two resistance, remember this thing, it is important. Two resistances in parallel, one high resistance and one almost 0 resistance, the effective resistance will be 0. So, if the resistance is 0, there will not be any voltage here. V out for the upper half will be 0, but lower half this will be reverse bias as if it is not there in the circuit, and then that will appear. So, in that case a output wave shape of this kind will be there. So, these are the clipping circuits. Now, in these clipping circuits we were clipping one portion completely, but this is not always the case. We can use biased clippers, in which we can choose that which portions we want to clip. Here this is, look at this case, this circuit, a resistance, a diode with this polarity, a battery, a reference voltage is applied VR. We get the output here, this is the input is provided here and with some voltage Vi. Now, because of this reference voltage, this will not conduct unless the voltage here becomes in excess of VR. For all voltages less than VR, that means when Vi is varying, when Vi is less than VR, then this will be reverse bias, and we can analyze, we can draw the equivalent circuit for this and analyze that circuit, and we will find this equivalent circuit is this, because this diode is reverse bias. So, that will be showing almost infinite resistance. We can take out infinite resistance, and then this reference VR, this is Vi is less than VR. Let us analyze this by Kirchhoff's voltage law, summation of voltages in a loop. Now, let us assume that current I flows through this circuit. Here is V0, this is Vi, then we can write the summation equation. This is the voltage drop across this resistance, and then V0, this is plus minus, and this is plus minus, then apply for this loop minus Vi equal to 0, and since no current is flowing, so I is 0 and hence V0 is Vi. That means, for what will be the wave shape? Wave shape will be this. Where this is voltage axis, this is time or omega t, and this is VR. We can choose VR as we wish. If we want to limit at 2 volts, then this reference voltage has to be 2 volts. If we want to restrict it at 4 volts, then this has to be at 4 volts. So, this will be the wave shape, and these portions have been clipped. For the other way, it will conduct, because already this is in reverse bias, and superposition of this negative signal here will make it more negative negative voltage. So, that means as if this is not there. So, then this is simple circuit, and we will get that the output will be 0. Now, here we took in this case, why this will be clipped off, we can see that the equivalent circuit will be this. for any voltage Vi greater than Vr, this diode will be forward bias. Diode will be forward bias. So, this is almost as a short. So, this is shorted here and this is the reference voltage and this is Vr with plus V 0 and in this case V 0, this is shorted. So, this will be restricted, V out will be equal to V r. This is what we have shown here, that output is clamped at V r. I repeat and you understand this again, that this is the diode which is forward biased for all voltages in excess of V r, that the on diode has almost 0 resistance. So, this is ideally we have shorted it and then what you will observe here? You will observe here V r. So, this voltage is, this part is clipped and we get this way. If we wish, we can use this biased clippers in symmetric, so that this portion is also clipped. For that we will have to use 2 diodes and both are biased, and this is this circuit. This is VR1, VR2. Look at the polarity and the direction of the diodes, and here we get the output. Here we connect the signal Vi. If we want symmetric wave shape, then VR1 for symmetry, VR1 has to be equal to VR magnitude of VR1 is equal to the magnitude of VR2, and in this case the output wave shape for the symmetric case it will be this. This is voltage 0, this is VR1, this is minus VR2, and under this condition both will be identical, and we can here this portion has been clipped off. These portions have been clipped off. So, we can restrict the magnitude of the wave. This is the topic which is covered in wave shaping, as I said earlier. And these clippers find by wide application. Briefly, I talk about clampers. What is the purpose of the clamper? Let us see here. Clamper circuit. First, let us look at the principle of clamper, that if there is a wave like this, where this is voltage and this is time axis and this is plus Vm, this is minus Vm. If this passes, this is applied to the clamper, this is the clamper, then here this is ground, one terminal is normally grounded, we get the output here. Then we can change the DC level. So, the output here we will get like this. Ideally, we will get where this is voltage axis, this will be equal to 2 Vm. That means, we have added almost a DC level for to this signal to shift the reference. So, this is 0 and this is 2 Vm. So, this is a clamped wave. So, this is the clamping action, very widely used in circuits wherever we want to shift the DC level of a varying wave. And one circuit I take, that here this makes use of a capacitor, a diode, and here is the load, and here we apply a AC wave like this. Now, what will happen at the lower half? This will act as a short. So, the current will flow, and if we have here a voltage Vm, then for the lower half this is Vm minus Vm, this will charge the capacitor, and this capacitor, this polarity of this minus plus, we are talking what happens in this lower half. This will forward bias the diode, and the capacitor is charged. This is short diode and this is load, 0 resistance. So, nothing will appear, but the current will flow here, and this will be charged with this polarity. And at the positive half, this will act as a battery now, almost as a battery, and for the upper half, this Vm plus this is having peak value of Vm, the two are added, and at the output we will get a wave shape, a wave like that. Like that, that is better drawn. This is almost equal to 2 Vm, and this way we have shifted the level of the wave, very widely used clamper circuits. So, this way we talked about some of the applications of diode in a circuit, and these are basically three most widely used applications. One is in rectifier. Rectifier circuits are required in every electronic device, and most widely used circuit is the bridge rectifier with pi filters. If we want to reduce the cost of filter, then often a shunting capacitor is used, and that is capacitor filter is used. And then we talked of clipping and clamping circuits, which are used for wave shaping purposes, and we can cut symmetrically a wave, we can restrict the upper magnitudes, and so that is there. And in clampers we can change the DC level, we can add DC in either way. If we reverse the role of capacitor and diode, then it can be done in the other way also. So, these are clampers. So, this was the unit. We finished the first unit, and that is on PN junction. We talked about the physics and the physical processes involved in the junction formation, and then through potential energy diagram we discussed how the currents will flow when the diode is forward biased and when it is reverse biased. And then we talked about the properties associated with the junction, the contact potential, very important, and we derived an expression for that. Then we talked variation of depletion width, and we also talked about the junction capacitances. There are two capacitances. In forward bias there is a in the reverse bias there is transition capacitance, in the forward bias there is a diffusion capacitance, but in forward bias the effects of the diode are dominated by the current flow, while transition capacitance plays an important role when the diode is reverse bias. And then we talked about these other circuits. So, that completes our unit on PN diode.